We've got two folks with us here today from USDA, Jason Nemecek and Jerry Mohnhaupt.
Actually, three.
Three, so the third, who's our third one? Oh, Adolfo Diaz, okay. Awesome. So I'm really looking forward to hearing about this. I've been sort of watching from a distance as the USDA has been building out their soils hub. It's, what's the word I'm looking for? It's an ambitious take on really large scale land cover analysis and soils analysis. It's pretty darn cool. So who is speaking to start with? Jason, Jerry, and Adolfo?
Sure, I could start out. Thanks, Paul. My name is Jason Nemecek. I'm the National Soil Data Application Scientist for USDA. I'll let Jerry introduce himself and then Adolfo.
Mohnhaupt, Geospatial Coordinator for the Hub.
Good afternoon, everyone. Adolfo Diaz, GIS Specialist with the National Soil Survey Center. And I've been working on the Hub for the last 3 months. Primary duty is to try to bring in as much high resolution elevation data as we can into the Hub.
Take it away, Jason.
All right. So what we're trying to build here at USDA is a dynamic soil modeling platform, essentially for helping us do predictive modeling. We have a wealth of soils information, wealth of data for soils information that has very good metadata for data dictionary and scientific metadata associated, lots of points on the ground, and our soil Sergo information. And the Dynamic Soils Hub is essentially a flagship innovation environment for scientists to model and report on soils data with conservation management. So if they're applying certain conservation practices, we might be able to predict some benefits, soil benefits based on those conservation practices, or look at the conservation practice points and look at kind of results based on conservation management. Our NRCS scientists are charged with scientific modeling and decision support for leadership that often lacks access to the raw data and tools to help us visualize and improve information to leadership for conservation outcomes. Next slide, Jerry. And I'll turn it over to you.
So obviously getting into the PostGIS side of things, a lot of our soil scientists, they spend a lot of time trying to gather the data to do the analysis that they want, and they spend way too much time trying to clip the data to their AOIs and try to get it running in their local environment. So we're trying to take that effort away from them by building these large data sets that are national so that they can focus on running the data, running their analysis and not having to prep the data. So we're also building dynamic tools, connecting all the data sources, the workflows, and high capacity geospatial processing. Obviously, our server is 64 CPUs and 512 gigs of RAM. So that's where we're starting, and we'll see where we get to when we start adding a bunch of users. So here's kind of an example of the interface that we're building now. We have a full range of users that some users are not familiar with Postgres or PostGIS, and they haven't really run any RStudio or done any R coding. So we're building an interface for them to be able to get into the modeling world. And but there's other people who are PostGIS experts, and they just want a Linux login and access to the database and just stay out of the way. So we're trying to be versatile and flexible so that the people who are beginners can be productive, but certainly stay out of the way of a lot of the power users as well. Currently, we're still building out the platform. It's an AWS. We're developing that user interface that dynamically develops the models and can integrate all the PostGIS and our modeling and basically hit several different systems from one interface. And we're building out the data pipelines and analysis pipelines as well. So we're supporting the soil and climate scientists as data stewards. So when we take their data and put it into our environment, that database belongs to them. And certainly the data doesn't get out of their database until they create authoritative data and decide what could be shared. Also trying to meet the Geospatial Act, be in compliance with that, and meet our FGDC metadata efforts, which are, as you know, substantial. So here you can see kind of some of the analysis that we're trying to do here. And the way I like to think about this is our friends at the USGS do a really good job of mapping where all the water flows in the rivers and the lakes. And we're trying to map where the water flows everywhere else. So by building these high detail elevation models, at least on a smaller area, we could start building these 3D terrain models and start mapping how the data flows over the terrain based on all sorts of parameters. So here's our study area, all states, and certainly we got Palau, Puerto Rico, so it's a very large area. So trying to manage standard data sets like land use data sets, the data sets are very large, and so we can't load up all of the data into the database for this whole area. So that's why the techniques we're using to integrate the raster data that sits outside of the database into the database is so valuable, and why we have a very specific architecture is we have a very raster intensive environment where we want to provide just terabytes of data and hundreds of layers of raster data, but we don't want to import all that data into the database. So, and if we tried to do that, it'd be just way too much data in the database. So here's our tech stack. So we're definitely open source. Obviously PostGIS and PostGIS. So a little bit different. Pretty much NRCS was a SQL Server Esri-based environment. So we're one of the first teams to go to PostGIS and Postgres. So it's definitely, breaking ground for a lot of these new technologies within NRCS. So here's our database architecture, currently running 14.3 and PostGIS 3.1, and it's installed on a EC2 instance. So there was some pressure to go to Aurora or a relational data service, but we had dependencies on the EBS volumes. And for those that don't know, what EBS volume is just like a disk drive that you attach to a server. So just storage that acts as a disk drive. And we are, installing multiple EBS volumes, each with 16 terabytes each. And we're putting data across all those different EBS volumes so that we can make that data available to users without having to load that data into the database. So we were also looking at cost optimized GeoTIFF files and did some benchmarking, and they were considerably slower. And obviously, we're working with such huge data sets that we have the need for speed, and just having to go through a massive data conversion process to take all of our raster files and convert them into cog files just to have them run slow in an S3 bucket really wasn't worth it for us. So we may do that for less priority data sets here in a few years. But for right now, we're trying to fill up our EBS volumes with priority data sets so we have performant access to it. We also didn't want to be tied to the version of PostGIS and PostGIS that AWS supports. And we all know how frustrating that is when, Paul and Crunchy come up with, exciting new technologies, but you don't get to take advantage of them because your Aurora version is a year behind the latest technology. So we didn't want to be stuck within the framework of what AWS provides. So we installed Postgres on a EC2 instance so that we can control the versions of Postgres and versions of PostGIS and all the libraries ourselves. So one of the main technologies that we're using is this Raster to PG SQL. And it's pretty critical to our workflows because, like I mentioned, we have so many thousands of raster data sets and they're huge. And this is a great way for us to make all that data available to our users without having to load it into the database. So we're using this remote flag, which basically we teach the database that remote raster data set is kind of part of the database. And when you run this command, it basically creates a table in the database that's the spatial index to that external raster data set. So it allows us to have access to, very quick access to that external raster data set without having to load it. Now, one of the tricky things is this tile size. So in this particular example, I chose a 56 by 56 segment of pixels within this particular raster data set to represent the tile. And thanks to our friends that were helping us out at Crunchy Data, we determined that this 56 by 56 tile size for one band image gets the best performance because it matches a page size. So certainly for the smaller data sets, we can use this small tile size. But when we're talking a 40 gig image with this raster, with this tile size, it's still a billion records. So we'll have to go a little bit larger for our tile sizes, like 560 by 560 pixels per record, just so that we can reduce our record count when we're working with these very large data sets. So every time we try to pull a tile or a collection of pixels out of that external raster data set, it would fill up 10 pages. And hopefully we'll get, it's a good balance between reducing the amount of records we have and still getting enough performance to pull the data off of those external raster data sets. So here we see an example of when we run the Raster to PG SQL, it creates this composite data type called Rast. And optionally, you can include the raster data set name. And this was working for a while, but I found that when you try to do an intersect, so we're trying to take an area of interest and intersect it with this particular table, there's a performance penalty with trying to convert the geometry out of the raster field. So to speed that up, I calculated a geom field from the raster field. So when I'm trying to do a spatial selector, the ST intersection, I use the geom field. And then once I have that selection made, I do the dump as polygons or pull the pixels out of that raster using the Rast field. So and that really speeds up performance because when we're doing that, the ST intersection, it's not having to calculate the geometries out of this composite field to do that spatial intersection. So that really speeds things up. So here's a sample analysis, potential farmland loss. And this is 12 in northern Denver. And between 2001 and 2019, there was a lot of urban sprawl. And so I wanted to just demonstrate how we could pull pixels out of those external raster data sets using just, in this case, a watershed boundary. So it's only less than a minute to pull these pixels. And of course, this is a national data set at 30 meters. So it's about 4 gigs in size. And it takes less than a minute to select the pixels out of that raster image that's external to the database, convert them into polygons, and then flip them to this AOI. So here I did that for the 2001 national land cover data set, and I did the same thing for 2019. So between 2001 and 2019, due to urban sprawl, in other words, these blue areas used to be farmland and now they're a subdivision. And over that time period, we lost 513 acres of potential farmland to urban sprawl. Now that I have this process built up, I can run it anywhere in the US without having to do any data management, because the process is pretty well automated, and the process for extracting out the pixels and converting them into polygons is very quick. So one of the benefits of this technology is, in this case, we use this climate data from the Prism Climate Group out of the University of Oregon, and every year they publish updated data, or they have data that gets updated daily as well. For a lot of our purposes, we have this either monthly or annual data, and if the pixel height, the width, and the band configuration, in this case there's one band, stay the same between data publishing, then it becomes very easy to maintain the data, because all I need to do is go delete this particular image off the EBS volume and put the new image there. And as long as it's called the same thing, and the pixel height and the pixel width and the band configuration is the same, that's the extent of data management. I don't need to reload the data. I don't need to rerun the Raster to PG SQL. So that saves quite a bit of time to keep updated data available to our users without having to run big database queries to update tables that are in the database. So that's a very valuable aspect of this particular architecture. So here's an example of some of the sizes of the data sets that we're working with. So you consider it's 40 gigs out of a single TIFF file. That's several trillion pixels. So it's not really feasible to load up these particular TIFFs into the database. So this Raster to PG SQL with the remote flag is really the only way to make this data available to our users via the database without having to load it up into the database. And this is where we start to see all sorts of benefits, because we literally we're going to start with 200 or 300 terabytes of data that we'll make available to our users, and they pretty much don't even need to know that that a lot of this data is external raster data sets. Either they can figure out how to run the intersect and extract that data out as either pixels or polygons, or we could do it for them. So at least for the elevation, here are some of the parameters we're trying to collect. So, and you can see it's pretty interesting from a scientific aspect of everything we're trying to capture. And this is just the elevation data. This doesn't include the climate data or the conservation data or the soil data. But what's nice is that when our soil scientists come into this environment and they want to start a new project, they basically just have a shopping cart of what they want, right? They want elevation data, or they want solar radiation, and they want annual precipitation, and they want the soils data. Well, it's very easy for us to go through and clip that data out for their study area for just the parameters that they're asking for. And, it takes, depending on the data, several minutes or maybe an hour to prep all the data for that particular user or that group of people, so that they're focused on the science. They're not focused on trying to collect all this data, get it into a state that they can use it for their analysis. So that's when we start to see the value of using this particular architecture. So because they're focused on science. We're also trying to build these standardized reference cells, and we chose these cell sizes based on the size of the data products that we wanted to produce. So we're going to be publishing data out as 120 meter, 30 meter, 10 meter, and 3 meter is what we'll be doing a lot of our elevation analysis with. So when we're doing terrain analysis and overland flows, we're using this 3 meter standard. So right now I'm building out all these grids, and each of the smaller grids will have the cell IDs of the larger grids, so that we can start doing spatial analysis simply by running either aggregation or deaggregation using integers. And basically we can start doing analysis on larger areas because it's just a database query using integers. And we get a lot better performance that way. As we know, databases are very good at processing integers that are indexed against each other. So we're trying to take advantage of that. But the other thing I'm excited about is we're trying to standardize the way we, all these different groups conflate the data together. So, we get scenarios where 2 scientists share data with each other and they do the same analysis, but they get different results because they conflated their data differently. So instead of having them both conflate the data differently, we ask them to conflate to our standard grids, so that not only are their data sets conflated against each other, but they're also conflated to all the other data sets that we've got conflated to this standard. So one nice thing about that is, as we have different research initiatives, there might be, East Coast research initiative that's doing elevation data, and another that's doing soils initiatives, but they leverage our standardized grids. Well, in 2 years' time, when they're producing data products from their research initiatives, we don't have to conflate their data together and produce more data because their data is already conflated together because they're using these standardized grids. So that's what we're trying to achieve. Obviously, we can't force anybody to do this, but we at least want to present these standardized grids in both raster and vector formats so that people can conflate to them as they need to. So here's some more sample analysis, and I know Adolfo, you've been involved with this as well, so feel free to chip in here. One of our initiatives that we're going through is a lot of the farms in the Mississippi River Basin apply nutrients, and then those nutrients run off their farms, and then they run into the Mississippi, and then they run all the way down to the Gulf of Mexico, and it's causing hypoxia in the Gulf of Mexico. So we have this initiative to help our farmers keep their nutrients on their farms and keep our waterways healthier as well. So, oops, let me go back here. So, Adolfo prepped this where we prioritize the watersheds by the cultivation amounts. And obviously, there's some of these watersheds that are almost 100% farmland. So we can, within the Mississippi River Basin, we can identify those priority watersheds where we want to really focus our efforts so that we're getting the biggest bang for our buck and helping our farmers save money by keeping the nutrients on their farms, but we're also helping the public by keeping our waterways clear or clean of those nutrients as well. So once we get our watersheds identified, then we're going to build these, high detail 3-meter digital elevation models or terrain models for that particular watershed or that particular farm or that particular county, whatever the AOI needs to be. And then, we could start using that to model individual farms. So here we got an example of, we want to help our farmers figure out how to build terraces on their farms so that the nutrients go into the terraces and then go to the next terrace instead of just running out to the river, or potentially build these waterways or wetlands to filter out those nutrients before it goes to the river. So, that's one of the efforts that we're trying to support. Now, one of the problems we have with this data is what we refer to as hydro enforcement. And for instance, this particular 2 farms, if we were to just use the elevation data, it would show that there's a berm where this road is between the 2 farms, but there are actually 3 culverts between the 2 farms. So the water is freely flowing between these 2 plots of land. So, we're going to be going through a hydro enforcement effort to take those culverts and potentially on the fly alter the DEM or the terrain data set so that the actual flow of water in the field is actually represented in the models that we're building. So, that's a pretty substantial effort trying to do that on a national scale. So that's something that we're hoping to do. We'll see how far we can get that and how much integrity we could build into that analysis by doing accurate hydro enforcement. Another thing that we're doing is these analysis pipelines, so the shape curves, soil health curves. We want to support multiple shape curves, so different applications like that conservation desktop. They may submit a lat long to our environment, and then we'll return a shape curve so that they can see the soil health of that particular latitude, longitude in their application. Some cases they may submit a latitude, a longitude, and a variable related to how much of a particular nutrient there is. And then we could take that input as well and calculate a custom shape curve for that particular analysis. So we're planning on having multiple shape curves just depending on what gets requested. So that's kind of what we consider to be analysis pipelines, is an API that just produces graphs like these that show the soil health at a particular point or a particular polygon. So that's kind of it for now. We've also got all these data sources, but maybe we can talk about any questions you guys might have.
So I got one question in the Q&A from Raj Talati, Raster to PG SQL. You just copy metadata into the DB, and if so, how is the geometry of intersection pulled in? Was John's size of this table too high?
So if I go back to this example, so here we have when I run the Raster to PG SQL, you have control over the size of your tiles. So here I'm choosing 56 by 56 just to demonstrate that, that's the most performant tile size. But that also leads to a lot more records in the table that you're generating if you're working with a 40 gig data set. So if that 40 gig data set has 20 trillion pixels, that's still a billion records that you end up with your Raster to PG SQL. So by increasing the size from 56 by 56 to 560 by 560, you're reducing your record count by that much. So you kind of have control over the spatial index table, what this Rast field represents. So the pixels don't actually exist in the database. This is just a pointer to that collection of pixels. So, and then we figure out from this table the subset of records that we want to grab pixels from. And then we use this Rast field to pull those rasters either as pixels or convert them to polygons into the database as needed, or just in memory with a select query, just depending on your analysis. Did that answer your question about the metadata? Look at the Q&A here.
Yeah, we're gonna have to hope so. So it's coming up to the top of the hour. So I'm gonna say thank you very much, Jerry and Jason and Adolfo, for your presentation this afternoon.